Okay, so in this chapter, we are covering radical reactions. Um, the main difference between radical reactions and the other reactions we've been doing is that in everything that we've done so far, there was always a Lewis acid, Lewis base type interaction. It was always based on some sort of electrostatic interaction where there's a large electron density and another area that has a lack of electron density. Electrons were always moving in pairs to make and break bonds or to show resonance. All of our mechanisms were drawn with double barbed arrows. And in these types of mechanisms, bond breakage is called heterolysis. Radical reactions work a little differently. This is called homolysis. So one electron from the covalent bond between two atoms goes with one atom, the other electron goes with the other, and we used single barbed arrows to demonstrate that. And your result is that you have an atom that has one unpaired electron and another atom that has one unpaired electron, and this is called a free radical. Radicals, again, are reactive intermediates. They're not the final product of the reaction. So typically, this is the first step of the reaction, the step that actually initiates the reaction, which is why it's called initiation. And then there are three total steps to any radical reaction. There's initiation, propagation, and termination. What we'll see is that there's usually one type of initiation. There can be multiple types of propagations and multiple types of terminations in any reaction. So two of the types of radicals that we looked at yesterday were alkyl radicals. Excuse me. Alkoxyl radicals and halogen radicals. So in order to form an alkoxyl radical, you will start with a dialkyl peroxide. So remember, peroxide is the name for an oxygen-oxygen bond. And then if you add heat or light to a dialkyl peroxide, the oxygen-oxygen bond is very weak. So homolysis will occur very easily and you'll end up with alkoxyl radicals. So notice the single unpaired electron. We still have lone pairs on those oxygens. That's not changing. We're not affecting that. But we gave this oxygen one extra electron and this oxygen has one extra electron. Notice also that does not create a charge on the oxygen because a negative charge is made up of two electrons. And a positive charge would mean that you're lacking two electrons. Halogens can do the same thing. So if you have a molecular halogen, such as bromine and chlorine, those are going to be the ones that we do this with most often. You can add heat or light, and you can end up with two equivalents of the halogen radical. So that was, I believe, all that we covered yesterday. Excuse me, sorry. So in homolysis, a covalent bond is cleaved and two electrons are divided equally amongst the products, right? So you have two atoms connected together. It could be two alkyl groups, even in the right scenario. You'd have to have an initiator to accomplish this. And it breaks up into two radicals. The likelihood of this occurring is based on the bond dissociation energy, which correlates to the bond strength. The bond dissociation energy is a term that you've heard before when you learned about calculating the enthalpy of a reaction. The enthalpy change of a reaction was calculated from the bond dissociation energies. You took the energies of bonds that were broken and energies of bonds that were made and added them together to figure out the delta H. So these values are positive for bond formation and negative for bond breaking. Just for reference, the hydrogen-hydrogen bond is a fairly stable bond. The bond dissociation energy for a hydrogen-hydrogen bond is 436 kilojoules per mole. But for chlorine, it's 243 kilojoules per mole. So you can see that this bond, it does not take as much energy to break this bond. So the bond dissociation energy literally means how much energy would be released if you were to dissociate this bond, or how much energy needs to be put into it. So the lower this number, the more likely the bond is to cleave by homolysis. So I want to talk a little bit about the geometry of carbon radicals. We know that carbocations are planar, and they're sp2 hybridized. And we know that carbanions holding an extra lone pair are going to be, the molecular geometry will be pyramidal, the electron geometry would be tetrahedral. The radical is kind of somewhere in between, because it's this, carbon has no lone pairs. This one has a full lone pair. A radical has half of a lone pair, so it doesn't take up as much space. But they are considered to be sp2 hybridized because they're a little closer to that than to being pyramidal or tetrahedral as far as electron pair geometry goes. The unpaired electron is still going to sit in an unoccupied p orbital. And that's kind of the key thing here, is that when you have a carbanion that's pyramidal or tetrahedral with the electron pair geometry, you don't really have an unoccupied p orbital. But in this case, we kind of do. So we're going to start doing the reactions with radicals. Most small radicals are highly reactive, so they are really, really good initiators and good at terminating reactions as well. Radicals will react in order to pair their unpaired electron. So it's like they're all running around with half of what they need, and they're looking for their soulmate. They're trying to team up with somebody else who has an unpaired electron to stabilize themselves. If a radical reacts with a non-radical, so just a regular molecule, a new radical will be formed. This is called propagation. And if a radical reacts with another radical, a covalent bond is formed, and the radical is killed, which is called termination. Are there any questions so far? We're going to look at these mechanisms step by step in a second. So if right now you're just waiting to see a picture that's coming up, I promise. The relative stabilities of radicals mirrors the stability of carbocations, which is nice. So a tertiary radical is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl radical. And it's for the same reason. Hyperconjugation is going to help stabilize that unpaired electron. And also because of the bond dissociation energies. The bond dissociation energy is also related to the hyperconjugation. If you have a carbon-hydrogen bond on a methyl group, there's not as much hyperconjugation stabilizing that. But if you have a tertiary carbon atom, you have the hyperconjugation of overlap with the other carbon-hydrogen bonds around here. And that can help stabilize the intermediate as you form the radical. Okay, so this brings us to reactions of alkanes with halogens. And you are reading that correctly. Earlier when we talked about alkanes, we said pretty much the only thing you can do with them is set them on fire and use them as fuel. That's still pretty much true, but you can do some reactions of alkanes with halogens, but they're radical reactions. So if you take an alkane and you react it with a halogen in the presence of heat or light, you will get an alkyl halide and an equivalent of the halogen acid. This only works with fluorine, chlorine, and bromine, so you won't see this reaction with iodine. We're going to look at this in detail now. So there's kind of a problem with this type of reaction, and that problem is that it's not particularly controlled, especially in the case of chlorine. It turns out that the chlorine radical is completely insane. It's highly reactive. So if you take a molecule such as methane and you react it with chlorine in the presence of heat and light, you're going to end up with a whole mix of products. You're going to end up making chloroform, you'll have dichloromethane, you'll have trichloromethane, and then, chloromethane, dichloromethane, chloroform, and carbon tetrachloride, which was actually used in, or you could say tetrachloromethane, but carbon tetrachloride is the name that was used for a long time when this compound was used in commercial dry cleaning. And then it turned out that it's a pretty serious carcinogen. And so it was pretty quickly pulled out of dry cleaning after that point when that was discovered. And then hydrochloric acid as a side product. The other really interesting thing about carbon tetrachloride is that it's incredibly dense. And my lab mates in grad school, I joined a group that was majority boys, and they did a lot of really stupid boy things. And one of the things that they liked to do was what they called the pinky test, where you would pick up an entire carboy of something with your pinky. And you guys have been in a chemistry lab, like, like a carboy is one of those big containers that you would get sodium hydroxide or acetic acid from in Gen Chem 2, like something where there's just, it's quite large, multiple gallons, multiple liters. Now, the thing is that if you pick your solvent with a little thought, it's not that hard. So like picking up a carboy of acetone, which is very not so dense, is actually pretty easy. But they're like, you should pick up carbon tetrachloride with your pinky. And I was like, I'm not an idiot. But apparently that's something that one of the guys did do and almost broke his pinky because he did lift it pretty high and then it just kind of like fell off, and they were lucky it didn't break open. But anyway, that's what I think of every time I think of carbon tetrachloride and the fact that it's dense. Okay, so this is the kind of messy outcome that you'll get from doing a reaction with chlorine as a radical. I'm going to go through the mechanism now just because it's kind of hard to understand where those products come from if you don't know the mechanism. So in the initiation step, you have chlorine. Sorry, I'm going to draw this out for you as well. You have your molecular chlorine and you introduce light. One electron is going to go with one chlorine atom. The other electron goes with the other chlorine atom. That gives you two equivalents of the chlorine radical. So that's our initiation step. Initiation is just the part where you are creating the radicals that are going to literally start the reaction. Our next step is propagation. So a chlorine radical is now going to react with a molecule of methane. And this part is the kind of confusing part of radical chemistry. So the chlorine molecule or chlorine radical is going to abstract a hydrogen. And when they do this, basically the bond is going to form in between the two of them. So this radical and this electron are going to form a bond between the chlorine and the hydrogen. The other atom from this bond is going to get put onto the carbon, which creates our alkyl radical. And I'm going to draw these bonds as Lewis dot structures so that we can keep track of all of our electrons. Okay, so that gives us our methyl radical. So this step is called propagation because we did manage to use up a chlorine radical, but in doing so, we created a new radical. So any step that creates more radicals at this point, that is not this step, is considered a propagation. So there are a couple of things that can happen here. The most important one is that the methyl radical, let me see, did I draw this next to N? Yeah, I did, okay. So the methyl radical is going to react with a molecule of chlorine now. So we're going to take one of these electrons, create a bond between carbon and chlorine. So this is the bond that we're creating. And then the other electron in this bond goes to the chlorine. And this gives us a product. Sorry, I said I was going to draw Lewis structures, so we'll do it that way. Plus another chlorine radical. Does this make sense so far? So I think the thing that most students struggle with is drawing the arrows correctly to indicate the bond formation. So you kind of have to picture that you're taking this electron and putting it into the space between the carbon and the chlorine, and the other electron is also coming into that space, and they're going to form a bond that way. And then our last step is termination. So you could also have a methyl radical react with a chlorine radical. To give us chloromethane. Now, if you're going to create some of the products that have multiple chlorines, what would happen is after this was made, another chlorine radical, ooh, that's so crazy. I never understand how that happens. And why it won't let me erase it, I don't know. So this molecule could react with another chlorine radical. It would start basically back up over here where you abstract one of the hydrogen atoms and you create another radical, but we would have a chlorine in the place of a hydrogen, and it would just continue. Are there any questions about this mechanism before we move on? No questions? Okay, if you think of one, let me know.
One question. So you're just like, you can just assume there's more chlorines and stuff in solution.
Yes.
Okay.
Yeah. So, I mean, looking at this, like one molecule of chlorine broke apart because of light and reacted with one molecule of methane. So the other molecules could all be doing totally different things at this point. We used another chlorine over here because not all the chlorine is going to immediately break up by homolysis. That's not necessarily the most favorable reaction. So you have to imagine that small parts of the reaction are reacting at a time.
That makes sense. Thank you.
Mm-hmm. So the summary of a radical mechanism. So your first step is initiation. You have homolysis of the chlorine molecule. The chlorine radical is formed. In propagation, there are a couple different types of propagation. A hydrogen atom is abstracted. Hydrochloric acid and alkyl radical is formed. Halogen atom can be abstracted. Covalent bond formed between alkyl radical and chlorine atom. Chlorine radical formed. So this is for every one of these things that's written, there's a step on the previous page. And then termination, alkyl radical and chlorine radical form covalent bond. Radicals are consumed. Now, the other thing that can kind of happen as a termination is two chlorine radicals find each other. But as long as you are still exposing the reaction to heat and light, any molecule of chlorine that's formed will eventually get used up. So radical reactions can be called chain reactions because each step generates the reactive intermediate required to initiate the next cycle of the reaction. So in doing a halogen atom abstraction, you create another chlorine radical, or in doing the hydrogen atom abstraction, you create the alkyl radical. So each step, except for a termination, creates the reactive intermediate required for the next cycle of the reaction. Okay, so we're going to talk about the reactivity and selectivity of a couple of the halogens. The first one we're going to talk about is chlorine. Chlorine is highly reactive and therefore very unselective. What that means is it's not going to discern between the most stable radical and the least stable radical. Chlorine is so reactive that it will just react with anything. You can kind of think of this as like, say you had to fast because you were going to do a blood test or something at your doctor's. When you are done with that, especially if your appointment was at like 3 or 4 p.m. and you've been fasting all day, you don't care what you eat. You're going to eat whatever is put in front of you because you are so hungry, right? And that's kind of chlorine here. It's highly reactive, it's unselective, it's going to react with anything. It does not discriminate between primary, secondary, and tertiary hydrogen atoms when it comes to hydrogen atom abstraction. It's going to create whatever radical it wants. So when you react with chlorine and light, there are two different types of hydrogen on this molecule. We have the tertiary hydrogen and we have a primary hydrogen. The tertiary one would create the much more stable tertiary radical. But chlorine does not care. It's going to actually pull off the primary one more often just because there are 9 of them. And so it's easier to get to it. But it also makes a pretty good amount of the tertiary product because that is the most stable one. So that one's also very likely to form. You'll also get a whole mix of the polychlorinated products in a reaction like this. There would be very many of them because there are so many different hydrogens. You can polychlorinate here in a bunch of different ways. And you'll get hydrochloric acid. The exception is that if you react what's called neopentane or 2,2-dimethyl propane with chlorine and light, there's really only one possibility, and that's that you would chlorinate the methyl group. You would still end up with some of the polychlorinated products, but since there's only one type of hydrogen here, you're only going to get one possible mono-substituted product. Does that make sense? Okay. Now, bromine is much more selective. Bromine maybe had to fast overnight, but they had their doctor's appointment at 8 a.m. and now it's just time for breakfast. They might be a little more selective about what they eat. So reactions with bromine will go through the more stable or more easily, which is usually also the more easily formed radical. Must have heat and light. Because it's less reactive, it has to have a lot in order to force it. So if you compare this reaction to the one that's on the previous page, when we did this with chlorine, we ended up with mostly this, some of this, and then a whole bunch of polychlorinated products. With bromine, you add in light and heat, and you're going to get the majority this product and a trace amount of the product on the primary carbon. And you're not really going to see poly halogenations with bromine. Are there any questions about the difference between chlorine and bromine? Okay, so we're going to talk about different types of radicals now. So far, we've only looked at just regular alkyl radicals. I'm going to remind you a little bit about the term allylic, because I think it's been a while since we've seen this. The allylic position references a carbon that is one removed from an alkene. So allylic, allylic, this would be an allylic halogen. So this would be called allyl chloride commonly. This is not the IUPAC name. Whoops, I put this double bond in the wrong spot. I'm so sorry. This double bond goes here. So this molecule should look like, and this bromine would be in the allyl position. Sorry, I'll fix this and send out a clean version. Now, the reason that this position is important is because the radical that's formed in the allyl position has resonance. So remember that the pi bond is made up of 2 electrons. You can form a new pi bond here. The other electron would end up on the end, and that gives you resonance of the radical. So remember, resonance is stabilizing. Anything that is more stable is also potentially more reactive. It's the more likely position for radical halogenation. So if there is an allyl position, that is where a radical reaction will occur. The allyl radical is more stable than the tertiary radical. This down here would be called the vinyl radical. This is very unlikely to occur. So the issue with the vinyl radical is that this is an sp2 carbon. It has more S character. It's a little more stabilized. That bond is less likely to be broken, and there's no resonance here to stabilize that either. So basically, you're just creating more electron density on something that is already experiencing a little more electron density due to the pi bond. So if you do a reaction with a molecule that has an allylic position, that is where the substitution will occur, and it'll occur there almost exclusively. Typically, you need to do this at a high temperature, and you usually use a low concentration of a halogen, so less than 1 equivalent. The reason why we'll talk about in a little bit, because you have also seen this type of reaction fairly recently in chapter 8, the difference being that there was not heat present. So The difference here is that if there is heat present, you will form a radical from your halogen, and you will end up with a radical halogenation product. If you do this at a low temp, so room temperature or lower, typically, you're going to end up with electrophilic addition like we saw in chapter 8. So the difference here, note the reagents are identical. The difference is the temperature. For the radical addition to occur, you would probably indicate something like 55 degrees C or higher. Low temp, room temp, or lower. Okay, there's also a way to do kind of a controlled bromination. You can do an allylic bromination with a compound called N-bromosuccinimide, or NBS. In the presence of light or peroxides, you will get the allylic bromination, and succinimide is your product. NBS provides a constant but low concentration of bromine radical in the reaction mixture. The initiation in this reaction looks different, but propagation and termination is more or less the same idea, and the outcome is the same. So I'm not really overly worried about you understanding how the initiation occurs, as long as you know what the product is going to look like. Any questions so far? Okay, we're going to do a top hat question. Let's go ahead and take attendance because it gives you some points. So the attendance code is 1007. Okay, I'm going to minimize this, but people can still submit. So the attendance code is down at the bottom right of the screen, 1007. So what is the major product produced in the following reaction? Remember that H nu, HV there stands for light. Okay, about 30 more seconds to submit. Okay. Okay, so we have a mix of ideas, but it looks like a lot of us got to the correct answer. So remember that in this situation, we have a double bond, so we need to look for an allylic position if we have one. So where would be the allylic position on this molecule? There's technically two allylic positions. All right, I'll label some carbons and you guys can give me a letter. Okay, which carbons would be in the allylic position?
Would D be one?
Yeah, D is one of them. Where's the other one?
B.
B. Can we do a reaction on B?
No. It's all substituted.
Right, it's quaternary, so there's no hydrogen atom abstraction possible. So any substitution that we do is going to have to occur on carbon D. Also, the important thing to remember about radical reactions with double bonds is that we do not lose our double bond. So that gets rid of 1 and 2 as options. Our double bond is going to be maintained. Number 3 is not a good option because they removed a methyl group, which is not something that we've seen. So the only one here that showed us the abstraction of a hydrogen, sorry, I almost knocked my computer over. Oh, my heart jumped up into my throat. Okay. This is the only molecule that showed us the abstraction of hydrogen and replacement with bromine and substitution in the allylic position. So answer 4 is the correct answer. Okay, we're going to switch back to our PowerPoint. You can still get attendance if you need to. It's down at the bottom of your top hat. Okay, so just like our allylic radicals, we also have what are called benzylic radicals. These are radicals formed in the, probably you're able to guess this, but the benzylic position. So the benzylic position, reminder, is 1 carbon away from the benzene ring. So this molecule here is called benzyl chloride because you have a chlorine in the benzylic position. So creating a radical in the benzylic position is highly stabilized through resonance across all of benzene's conjugated pi bonds. This makes it an extra stable radical and therefore the most reactive position because a hydrogen atom will be very easy to abstract from this position. So if you react a benzene containing compound that has hydrogens in the benzylic position, it will react with NBS in the presence of light to substitute in the benzylic position. So this would be benzyl bromide. You can also just react without NBS. Like you could do this with chlorine in the presence of light or heat. And you can put on 1 chlorine. You can do it again to put on 2, do it again to put on 3. Or you could add in a huge excess of chlorine in the presence of heat or light and get all the way to the tri-substituted position if you wanted to. You have to keep in mind there's not really any control with a chlorine reaction anyway. So if you used only 1 equivalent, you would probably actually end up with a mixture of all 3 of these. But if your end goal was to get to the tri-substituted, the easiest thing to do would be to just add in an excess of chlorine. Are there any questions about the benzylic position? Notice this looks a lot like the allylic position, right? You can see kind of the shape of the allylic position there as well. It's just 1 carbon removed from benzene, just like the allylic position is 1 carbon removed from a double bond. So I wanted to show you a little bit of a comparison. So if you had ethyl benzene, there are 2 hydrogens coming off of ethyl benzene. If you reacted with a chlorine radical, there's a chance that you could create these 2 different radicals. You could create the benzylic, which is the more stable, or you could create a primary, which is less stable, since it's removed from the benzene ring and not in the benzylic position. Now you react this with more of the halogen. It could be chlorine. Whoops. Okay. I think when I wrote this out, I meant for this to be X and not chlorine. So just any halogen, fluorine, bromine, or chlorine. The product you would get from this one would be the benzylic substitution. The product from this radical would be this one. This would be the major product. This would be minor. Realistically, if you were to do this experiment, you would probably get a little bit of both, but this would be by far the major product. So remember that when there are multiple radicals that could be formed, it's pretty likely that you'll end up with multiple products, especially with chlorine. With bromine, bromine would probably create just this and trace amounts of this. Chlorine would probably create both, but the top one would still be the major product. Are there any questions about the major and minor products here? Okay. So I want to look at the radical addition to alkenes again. So this is a little different. Previously, we had alkenes with X2, right? Molecular halogens. And we added in heat or light, and we maintained our double bond. Nothing happened to it. This is a little different. So remember that in chapter 8, we actually learned these reactions already. So in chapter 8, we talked about Markovnikov addition. Of a halogen acid across an alkene. So in this product, a hydrogen atom was added to the primary carbon and a bromine was added to the secondary. In the other reaction, we did an anti-Markovnikov. I really should have put the bromine on the other side. So if you like to keep your carbons straight, it would have come from this alkene, which is just the same thing. But so this is an anti-Markovnikov addition to an alkene. This is a reaction we've already seen. What we didn't know at the time was that this was a radical reaction. So you need a peroxide present to act as your initiator for this reaction. And then it'll propagate a new radical from the HBr. I think I wrote out the mechanism. Yeah. Okay, so we add in heat and we break apart our peroxide. Sorry, I hate the way I drew that arrow. Okay. So we break apart our peroxide into two equivalents of the alkoxyl radical. This is our initiation step. In the next step, the alkoxyl radical reacts with the halogen acid. To abstract the hydrogen and release a halogen radical. So we end up with an alcohol. I'll stick with Lewis structures for radicals. I think that's easiest. And the halogen radical. In our next step, the halogen is going to react with the alkyl group, and this is going to explain to us how the anti-Markovnikov addition happens. Where do we want the radical to end up on this molecule? Do we want it on the primary carbon or on the secondary carbon?
Secondary.
Yeah, it would be much, much better to end up with a radical on the secondary carbon. So that's how the bromine ends up creating a bond to the primary carbon so that the radical ends up on the secondary. Sorry, I 500% spazzed out a little bit there, but we're okay. There's our radical that we just formed. And then in our last step, we have our radical, we have some more HBr. We form a bond between the carbon and the hydrogen. Put the other part of the bond onto the bromine. And we end up with our final product. Whoops, sorry. Whoa, how did I accidentally, I pushed end, sorry. But we're okay. And this also creates another bromine radical to keep the reaction going. So we're not actually drawing out the termination step here. Do we understand where the anti-Markovnikov product comes from?
Yeah, that makes sense.
Cool. Okay, so this brings us to our next top hat question. Okay, about 10 more seconds to submit your answer. Okay, there's one person who hasn't submitted their answer. I'm gonna give you about 5 seconds. Okay. Okay, so most of us picked number 4, which is super. So let's take a look up here. Since we have a benzene present, what position should we be looking for? If we're going to do a radical reaction, what do we need to check if we have?
I'm trying to remember what you called it, but you want to go to like the closest carbon on like a methyl group or ethyl.
Right, so we're looking for a benzylic position, for there to be hydrogens in the benzylic position. And we have 2 benzylic carbons. One of them, just like in the last example, is completely substituted, quaternary. The other one does have benzylic hydrogens. So this is where we're going to do the reaction. So number 4 is the correct answer. I also want to show you guys there are a couple ways to eliminate some options. These are both kind of valid. Those are probably minor products. This one has a carbon with 5 bonds to it. We're not going to do that. So this is the correct answer. Okay, so that concludes our top hat usage for the day. Okay, so we only have 2 more slides left, and then we're going to be done with this chapter. And then I'm going to put up a practice problem on the screen. This is from a quiz that I usually give towards the end of the semester. It's a good one. It's a doozy. So, okay, so this last bit is just introducing the idea of polymers. There's usually a polymer question on the ACS exam, which you guys are not taking, but there will probably be one on your final exam. So polymers are made of repeating units of monomers. Monomer is just a term for an individual molecule that can be polymerized, covalently linked together into long chains. So for example, when ethylene is polymerized, it turns into just a very, very, very long alkane, which we call polyethylene. The main difference between polymers and small molecules is that polymer chains form significant entanglements. So what this means is that you end up creating a long alkane, and since you have many molecules of that long alkane, it's kind of the same effect as mixing up a bowl of spaghetti. So like when you have your like hard spaghetti noodles, you can separate them pretty easily, but when you boil them and like they're sitting in the water together and you go to pull them out, they're almost always tangled up, right? Unless you put like oil in there, which who does that, you know, because then the sauce doesn't stick. It's just not smart. But the spaghetti noodles get all tangled up, and that's the same thing that polymers do, and that's what gives them their very unique properties. So think of like, you know, your plastics that are stretchy but strong. That comes from the entanglements and interactions between the polymer molecules. So it's just showing you a couple of different ones. You have polypropylene. Polystyrene is the polymer that is more known as styrofoam. And then vinyl chloride can be polymerized to create polyvinyl chloride, also known as PVC. So the radical polymerization of alkenes is pretty straightforward. This is how a chain growth polymer is created. There are a couple different types of polymers, but we don't really talk about them too much in this course. But the radical polymerization is going to lead to a chain growth polymer, which means you have some sort of initiator, which is usually a halogen molecule, that starts by creating an alkyl radical. This is going to react with the next molecule of the monomer by radical reaction, which creates an identical radical, but just on a longer chain. And it just continues to occur until eventually termination happens. So maybe two chains find each other. So two chains with a radical on them end up finding each other, and that terminates the radical, or another halogen reacts or something, which is unlikely because there's not usually a lot of halogen present. Usually what happens is you end up creating multiple long polymer chains, then two chains terminate each other. Ultimately, the end result is a repeating unit of the monomer. So typically, the types of questions that you see on your final exam is it shows you the monomer, and then it asks you which of the radicals is the likely intermediate. That's the normal type of question. So for example, like in this one with the styrene, when the reaction happens with the initiator, you're going to have to create a radical here. It's an anti-Markovnikov type of reaction. So the halogen gets added to the end, and the most stable radical is formed. That's usually what you're looking for in this type of problem. Where is the most stable radical that can form? So not just what is the most stable radical they drew in the answer options, but what is the most stable radical that could be actually reasonably formed from the monomer? So that's kind of the shortcut for answering those questions. But anyway, that knocks off chapter 10 for us. So I told you guys that chapter is pretty short. It's 11:08, right? I do want to put up this practice problem because I think it's important that you see this type of problem before your quiz tomorrow, because I will definitely be putting something like this on your quiz. It'll just obviously be multiple choice.
I'm sorry, is the quiz tomorrow or Friday?
Oh, Friday, sorry.
Okay, thank you.
All right, sometimes I'm bad at days of the week. Specifically now. Like, are days of the week even real anymore? I don't know. Okay, so I'm going to give you an alkene, and then I'm going to give you several different reaction conditions. And these reaction conditions are going to come from many chapters. Okay. So this is your problem that you need to figure out. And I'm going to assign you to breakout rooms. Once you have them written down, please go to your breakout rooms and work on this. I'm going to give you until 11:20, and then we'll go over it as a group.